Yeah, so good evening. Today we will be discussing assignment number 9, and we are very close to the end of this course, power system analysis. Today we will be solving assignment 9 of the previous run, and assignment 9 is on economic load dispatch. So this is the last assignment on this. Probably assignment 10 and 11 will be, on these fault analysis, faults of on power systems, and the last one would be probably on that transient stability of synchronous machines. So I'll be sharing my screen. Yeah, I hope my screen is visible. So we will be again, as was the theme with the previous assignments, we will be looking at some of the typical questions of this assignment too. So let us first look at question 1. So the incremental, it says ki the incremental cost in rupees per megawatt characteristic of two generators. So the incremental cost in rupees per megawatt hour characteristics of two generators delivering 300 megawatt are as follows. So these are the two incremental cost equations. Incremental equation, so where P1 and P2 are in megawatt. So neglect losses in the system, so we are not considering any kind of transmission loss in the system. So they have stated for economic operation, find the generation P1 and P2. So the total, this problem is pretty simple. So P1 plus P2 would be 300 megawatt, because it is the two generators are delivering a total of 300 megawatt. And for economic load dispatch, we know that df1 dp1 equals to df2 dp2. So if we compare the two equations, we get the values of p1 and p2. So this would be your option number B. This was the first problem. Now going straight to the fourth problem. This is a pretty small problem, but a pretty, I mean, a important problem. So you need to carefully look at these two graphs and then solve it. So now this is a incremental cost curve for generator 1 and incremental cost curve for generator 2. So they have stated key the maximum and minimum limits have also been indicated. So 250, 450, 175 and 425. And so again we have to neglect any kind of loss, and then they are asking to find the optimum generation schedule. So for this, what you need to do, you need to plot these two lines in the same graph itself. So if you see, I have plotted this, and I mean from this you can see that our x-axis, y-axis is this incremental cost, this dfdp, and if you see for the maximum of G1 and G2. So the maximum of G1 is what? 450 megawatt, 450 megawatt, and the maximum of G2 is what? 425 megawatt. So your this thing, the incremental cost of G1 is less than that of G2, right? 600 and 800, and similarly for the minimum also 250 and 175, 250 and 175, the this thing is less, right? So 450 and 625. Therefore, I mean, considering these two, we have to consider the maximum, I mean, P1 to be the maximum of the upper limit of generator 1, right? Because it is from 250 to 450. Since the incremental cost of G1 is less than that of G2, therefore P1 would be 450. If this would have been for P2, that is DFDP would have been less for P2, then we would have considered P2 as 425. Instead, here we have considered P1 as 450, since DFDP is less for G1 as compared to G2. Therefore, we get P1, and if you solve for P2, 650 minus 450, it is 200 megawatt, which is your option number A. So this was question number 4. I hope this was clear, because I mean there was no differential. I mean equation was there, and I mean and you also can't equate df1 dp1 equals to df2 dp2, because clearly you can see these two lines are, I mean, not equal, right? So yeah.
Uh, I have a question here. Actually, we have the x and y coordinates, right? Why can't we find the equation of line, and then from that we can determine the dp1 by dc1, and similarly, sorry, dc1 by dp1 and dc2 by dp2. From that equation we can do that one, right? And find the slope, and then when we can equate both the things and find the value, because the coordinates are given. So why can't we derive the equation from the coordinates?
No, what do you mean by slope?
So difference in y coordinates, ratio of difference in y coordinate to the x coordinate, or it is the rate of change.
um, no, I mean, see, your y-axis is df by dp only, right? Incremental cost. It is not the
Yes.
fuel cost. So you have to equate df1 dp1, whatever equation you get, to that of df2 dp2, right? Then only you will get an equation, right?
Yes.
But when you try to solve that, what I found is that your p1 was coming more than this 450, this limit. So that is why this was the approach.
Okay.
Yeah, I mean you can try to solve that later, but yeah, I mean either P1 or P2. I don't exactly remember, but one was coming more than the limit. So that is why. And if one is coming more than the limit, then probably the other one would be less than that of the lower limit. So that is what this.
Okay.
Yeah. Okay. So now let us solve this question. So question number 5: a power system has two generating plants, and the power is being dispatched economically with, these are the two loads. I mean, yeah, sorry, power generation, I'm sorry, power generation at plant 1, which is 100, and 2 is 200 megawatt. So the loss coefficients are this. I'll come to this. Okay, so the additional cost to raise total load on the system by 1 megawatt is this much. Find out the penalty factor. So, okay, so for this, I would like to explain that what is penalty factor, then how are we considering the losses in the transmission line in this economic load dispatch study. So previously, I mean, we were, so this was the equation, right? So F equals to your Ft plus lambda times Pd minus n equals to 1 Pn, right? So where your Pn is the total, power being generated, and this Pd is the demand. Equals to 1 minute. Okay, yeah. Um, right. You, oh, sorry. You do this and then you equate this to zero and then you solve it. But now, I mean, we have a system like this, right? So let's say this is generator 1. We have a transmission line, and this is generator 2, and then again, yeah, this is generator 2, this is transmission line, and somewhere the load is connected. Let's consider this to be connected at 2. So we have this loss, right? So suppose your generator 1 is also feeding this load, and generator 2 is also feeding this load. So generator 2 won't incur any loss because of the transmission line, right? Because the load is directly connected at bus number 2. However, this has to, deliver the, what incur the total loss of this transmission line and then feed the power to this, right? So the whole thing changes now. So as a result, your this equation would look something like this, right? So lambda L, now P D plus PL. So this is the system loss minus your this thing, right? Now when you differentiate this, so uh, it would be something like this, right? So this, okay, because your demand is constant, right? This may vary, depending, PL may vary depending upon the current flow through the line, right? Depending on the generation. So that is why your PL is not constant. So that is why, we have a term del PL, del PL. Now, okay, so we are setting this to 0 as usual. So, okay, let me just simplify. This is very easy. So if I take this to the other hand, my this thing would be look something like this, and right, this would look like this. So this term, this whole term, right, this whole term is called the penalty factor. This whole term is called the penalty factor, or PF. And the generator whose penalty factor is more, obviously that would be, the fuel cost would be more and it would be generating less. To generate the same amount of power, the fuel cost would be more, right, for that system. So for any, any kind of system, be it a one bus system, so if there is a one transmission line or two transmission line, the PL is given by this formula. So summation, so there are basically two summations, and this is also from m equals to 1, and this is also n equals to 1 to yeah, so this is PM, B, Mn, then your Pn. So this Bn is that, as we saw in the last session, so G plus JB, right? So this is this coefficient B here, and we are again considering only the imaginary term, since we only consider since R by X ratio is very very small, right? So that is why we are only considering the. Now if we consider this two generator system, what would this PL look like? So this PL would be something like this, right? So your P1, then first we are keeping two n constant and varying this thing. Um, so let's keep n constant at 1. So this would be what your B11, P1, and then again we are varying m, right? So this would be what B21, P1, and then uh, this would look something like this, right? Right. Mm, yeah. Okay. Sorry. This would be, so we are keeping now m constant, and this would be varying, and yeah. So your equation would look something like this. B21 and B12 are the same, so that is where this 2 comes, and so this would be your net equation of PL for a two generator system. And this is this equation, as you see here, I have used this here, right? This equation. Now let's so what they ask to find out what is the penalty factor of plant one, right? So one minute. Yeah, so penalty factor, as we found out here, is this term, right? This term is the penalty factor. So we have to determine del PL del 1, and since they have asked us to find out what is the penalty factor of plant 1, so this would be 1. If it would have been at plant 2, so it would be 2. So that is why we partially differentiated with respect to 1. So we get this and we know every parameters, right? P1 is known, B1 is known, P2, B12 is also known. So you get this and you finally determine this PF1, which comes out to be 1.25, which is your option number A. So this was problem number 5. I hope this was clear. Pretty simple problem, provide you know this formula, how we derive it. So now same problem again. Now they are telling find out which uh, generator is contributing more towards the total system loss. It is pretty simple, right? Penalty factor for a, suppose there are 3 or 4 generators, so the penalty factor for that generator which is the highest, that would be contributing more, right? Because penalty factor comes from the loss in the transmission line, the due to the current flow from a particular generator. So that is why we find out the del PL del P2 for from this equation. So this is the this thing. So when we find out del PL del P2 comes out to be 0.625. Now your penalty factor 2 is 2.67. Clearly you see that, oh, this is PF2 is greater than 1.25, right? 2.67. Therefore generator 2 is contributing more towards the losses. So this was your question number 6. Now, I hope these two questions were clear. Okay. Um, yeah. Okay. So now let us look at question number 7. Now they are asking here, they are telling that the power system has two generating plants and the power is being dispatched economically with P1 100 megawatt and P2 200 megawatt. uh, Loss coefficients are this. Okay, same again, the same question. Now they are telling to find out the total load on the system for the given operating point, right? So the total load would be what, your P1 plus P2 plus the loss in the transmission line, right, due to the current flow from both the generators. Now loss equation we know, right? And we also know each and every term. Now when we put the values, we get it as 72.5 megawatt. You do this simple sum, so it comes out to be 372.5, which is your option number B. So this 5, 6, 7, these three were connected problems. I hope these three problems were clear altogether. Okay. Mm, now,
Previous one,
hello. Yeah.
uh, is it total generation minus losses is the demand?
Uh, yeah. Demand is that, but you have to find the total load, right? I mean, it is what your P1 is the total load power being generated, and your at one station 1 and 2 is the total power being generated at station 2, right?
Yes,
And
total
your,
generation is 300 megawatt.
yeah,
Demand, when you are calculating demand, so generation equal to demand plus losses. So Demand will be generation minus.
Generation equals to the total power in the system, right? So that would also incorporate the loss, right? So that is why your generation is always slightly more than the demand to incorporate that losses,
Okay.
right? I hope you got it.
Hmm.
Because you have a big transmission line network, right? When you flow current through that, that would be losses. So that is why, demand is fixed, and that is why you have to somehow vary your generation to meet the demand, right?
Hmm.
Okay.
I have a question here in this case. If
Yeah.
P1 and P2 are the generations,
Hmm.
that itself includes the loss, right? In it, 300 megawatt includes the loss in it. If I'm calculating 72 megawatt as the loss means, then the final demand should be 300 minus 72.5, right? Because they have stated the plant is generating 300 megawatt in total, which supplies loss plus the load. So
um
in that case, the load should
P1.
be, yeah, and I have identified the loss as 72.5 megawatt. So I'm going to subtract that from the generation, then I will get the actual load. But here, why we are adding that?
See, P1 is not the total. P1 is the power which is being generated only at station 1, right? The power which is being generated at any station after that via step up transformer, it is being fed to the directly to the transmission line. So P1 is that. Similarly, your P2 is that. Now, when you are flowing a current through a transmission line, you will incur some losses in that, right? So where will that losses go? You also have to incorporate that losses, right?
Yeah, I'm clear about that. What I'm
Yeah.
trying to tell is P1 plus P2, which is total generation, that is equal to
Huh.
loss plus the actual load. So loss I have identified as 72.5 megawatt. Generation is equal to 300. 300 is equal to 72.5 plus load. So load should be equal to 300 minus 72.5. That is what I'm trying to tell.
Mm,
Here they have mentioned already, they have given the generation. So generation is fixed. I'm going to take generation as fixed. Then I need to subtract the loss from it to find the actual load. It should be minus, right? Then
uh, yeah, you are right. Yeah. Your demand should be your total load minus the losses.
But the option is not there.
300 minus 72.5. Yeah, yeah, yeah. Because your equation also states something like that, right? Um, the total demand plus the total losses will be equal to the generation. Yeah. Mm. Yeah, you're right. Mm. Yeah, but the options are not there. Yeah, these guys do make a lot of mistakes while they're, forming this, because every year they change these kind of questions. They don't repeat these questions, right? Because these courses repeat every year. So while doing that, they make some mistakes. Yeah, I agree. This would be minus. Yeah.
yeah, okay.
Okay. So now, question number 8. In a two power plant system, the entire load is connected at plant 2, which is connected to plant 1 by this transmission line. I have drawn it here. Now, plant 2 supplies 104 megawatt directly to the load, and plant 1 supplies 102 megawatt of power with a corresponding transmission loss of 6 megawatts, right? So, your PL becomes 6. Now, calculate the penalty factor of 1. So as you see here, so this load is directly connected to bus 2, right? So any kind of loss in the transmission line would be only incurred by this generator 1 only, right? Because this this equation here, your B12 and B22 would be 0. Therefore, we would be only left with this term. Hence, your P loss would become something like this. So from here we are given the value of P1 and P loss. We calculate B11, which is this per megawatt. and now we simply differentiate this partially, and we get this as 0.118, right? And this is simple. Penalty factor would be something like this, 1.133, which is your option number probably D. Yeah, none of the above. Okay, so yeah, I hope this was clear. Now, so 8 and 9 is connected. So here they are telling to calculate the penalty factor of plant 2, right? Now, as we saw that the total losses, this PL is only due to that first generator, right? So, I mean, for the loss due to P2 would be 0. Therefore, I mean, this whole term, this whole thing would be 0, right? Therefore, your penalty factor would come out to be 1. Very simple. So, this would be what option number C. Yeah. So, okay. Now let us come to question number 10. Again, two generating units are there, and these are the two limits of power that they have shown. And okay, so for a certain demand P1 and P2, this DC1 DP1 is this much 89.5, and DC2 DP2 is 74. Again, transmission losses are negligible. If the generators are rescheduled to find the to minimize the total cost, then the ratio of P1 is to P2 would be what? So we have these two equations, and we know that P1 plus P2 equals to 230. Now, since they have mentioned here that the generators are rescheduled to minimize the total cost, therefore we have to utilize this thing, right? That we saw initially, DC1 DP1 equals to DC2 DP2. I mean, you can, I mean, one can, ignore this line and directly replace the value of DC1, DP1 to be 89.5 and 74. That would give the wrong answer, because they have clearly mentioned that they are rescheduled to minimize the total cost. So by doing that, by equating these two, you get your second equation, and by solving this, you get the value of P1 and P2, and when you divide it, it comes out to be 0.7796. This is your option number B. I hope this was clear. Okay. So now again, pretty simple problem again. A lossless power system has to serve a load of 300 megawatt, two generators with cost curves. These are the two equations are given. Now when PG1 and PG2 are the megawatt injections respectively from generator 1 and 2, find the minimum cost of operation. So again, so since they have mentioned the minimum cost of operation, again this thing has to be done, right, for finding out PG1 and PG2. So again, we know that the total load is this much. So your I mean, you get these two equations, you solve this, you get the values of PG1 and PG2. You again replace this back in C1 and C2. You get the values, and they have told key. Okay, where is the question? Find as follows: the minimum cost of operation, right? So it is the total cost, right? So C1 plus C2. So that is what I tried to find out. So it comes out to be 2424, right? Which is your option number D. Yeah. Now, so this is the last problem, probably question number 12. Yeah. So this is again a two generator system supplying a load of total load of 45 megawatt connected at bus 2. Now this C1 is this, C2 is this, and the total loss in the line, this is in per unit. This PG1 is also in per unit. Clearly they have mentioned PU. So where the loss coefficient is specified on 100 megawatt base. So the most economic power schedule is, so we have to find out what is the value of PG1 and PG2. So now, yeah, again, since this is this load is connected to this bus number 2, therefore the loss on the transmission line would be only due to the generator 1, right? So this is our equation. This has also been given here directly, right? Now, directly from this equation, we get B11 as 0.5, right? By equating that our parent equation with this equation. And when we differentiate this, so I am treating this P loss as PL here. So PL P1 is del PL del P1 is 2 P1 V11. And now, so I mean, for a loss, for a system with loss in the transmission line, our this incremental cost equation due to the economic scheduling would look something like this, right? Initially we had del C1 del P1 equals to del C2 del P2, but now we are incorporating this loss in the transmission line as penalty factors, right? We saw this. So this would look something like this. Now again, since there is no loss in that I mean no loss due to this generator 2, therefore your del PL del P2 would be 0, right? So we okay, so we know this. So 200 1200 and 1500 rupees per megawatt. So okay, so I have written this wrong here. So this would be del C1 del P1 and del C2 del P2, right? Because this is in rupees per megawatt hour. So I'll make this correction before uploading this file. Okay, so now from here we get our del PL del P1 to be 0.2, right? Now we knew this equation again. Now when we substitute this back, we calculate the P1, right, which is 0.2. Now our base is 100, so we get into 100, it comes out to be 20 megawatt. Hence our loss is what? 2 megawatt. Now could you please mute yourself? Yeah, okay. Yeah, so our total demand is, yeah, Lakshman, you were correct. So there was a problem in the previous, sum that we saw, question that we saw. So total demand would be what your the generating station 1 ka power and 2 ka power minus the total loss, right? So we have to find out what P2, right? And also P1. So P1 we found out P2, which is 20. So P2 is only remaining, and demand was given probably, right? Yeah, 45. So it comes out to be 27. So which is your option number C, 20 and 27. I hope this problem was clear.
Yeah, yes.
Okay. So yeah. I mean, these assignments, these problems are pretty simple provided you know the formula and all. And these are pretty small problems. So I hope you'll be able to solve the assignments very quickly. And yeah, this is a, there was a problem with this, right? Where, yeah, this would be minus. Clearly, this would be minus. So 300 minus 100. Okay, so this was all for this assignment. Okay, so for assignment 10, I won't be able to take the live session next Friday at this time because I am actually traveling out of India. So I have told the NPTEL people and I have rescheduled that live session to Saturday from 3 p.m. to 4 p.m. Okay. As only your assignment number 10, assignment 11 and 12 would be at this time only. So just a reminder, and you will be getting an email from them also, reminder of that. So this was all about assignment number 9.
And one more general doubt.
Hmm.
Can you go to the SLD of last drawing, last question, the representation? Yeah, yes.
Yeah, yeah.
Uh, Here I have a doubt. Like
Hmm.
PG1 we have, PG2 we have, and 45
Hmm.
megawatt is the load.
Hmm. Hmm.
How can you consider the loss is not supplied by the line loss is not supplied by PG2? Because with this question up to this limit, with this question, I
Hmm.
don't know what would be my generation at all at PG1. It could be even 1 megawatt. My line loss could be 5 megawatt. In that case, G2 has to supply the loss of line. So how we are under what condition or what basis we are assuming that the line loss is not supplied by generator 2, it is only given by generator 1. Let's assume you're generating again in PG1, you're generating 2 megawatt. I'm having line loss of 5 megawatt. So the balance has to be compensated only by PG2, right?
Lakshman, that would be a big loss, right? Normally in a transmission line, we don't get that amount of loss, right?
Oh,
1
I
megawatt it is
understood it,
generating.
but in the previous, I'm just stating it for example.
No,
Okay,
I
in
mean we
previous
have to
question
think
also,
practically, na. I mean, and this resistance, the resistance or inductance, it increases with distance. So that is why this loss is only incurred due to the generator one only. And there would be some loss in the this thing due to generator 2 also, but that would be far less than that of G1, right? Because you can clearly see, for the current to flow to the load, power only has to go through in this direction, right? From left to right, and also from
y-
for G2 from top to bottom, right? It can't go back. I mean, yeah, that
what what
will
what I am
happen.
what I'm
Yeah,
trying to tell,
okay.
if your generator 1 is very less, if it is generating very less
Yeah,
amount,
that would be
then
a
the
special
loss,
case. Fine. Then we have to increase the generator 2 ka generation, and then yeah, I agree.
uh,
That would be a
s-
separate case
since
altogether.
your yeah since initially we do not know it, what would be my
Hmm.
generation 1, we do not know it, what is the capacity of generator 1, we don't know it, but we are making that assumption, right? Directly we are stating it is the loss is not only going to be supplied by PG1, it is not going to be supplied by G2. So under what basis we are
See,
concluding
you
or
can't
taking that
say that
assumption?
we don't know. First of all, we know what is our demand, right? And we know that I mean, what quality of transmission line we are actually using. So every parameters we know. Based on that, only the generator 1 and generator 2 are, I mean, that would be fixed, would be installed, and then the power would be delivered. Something like that would only happen, right? Calculations are only done on
Okay,
that basis.
okay.
Yeah, I mean, load demand is fixed, and first of all, and I mean, secondly, your transmission loss would be what? I don't know exactly the limit. It would be something 0.2 or 3% of the total demand or something like that is there, right? So based on that only your generator 1 and generator 2 is chosen, right?
Yes. Again, if PG1, let us consider it as having capacity of only 5 megawatt, and PG2 is
Hmm.
having 60 megawatt capacity. So
Yeah.
it
Then we can't, then it
it
would
depends,
be
right?
a
It
different
may
scenario. Hmm.
the to meet the minimum or to minimize the loss or what is it, the
Yeah,
optimal
generator 2
generation,
has to
then
supply that. Generator 2 has to increase its generation. I agree.
okay, then
But
so
I mean, you can clearly see the generation of two these power plants, right? Generators. It's 20 and 27. They're quite close. I mean, it's not like 4 megawatt and 20
yeah.
megawatt, right? 4 megawatt would mean that there is some kind of fault in that system or something like that. Substantially, it has gone down. Something like that would happen, right? So
Okay, and
this line
PG1,
would complete.
PG2 here represents generation, right? And it is not mentioning the generating capacity.
No. It's yeah. Sorry, don't take like that. So wait, let me go to some other problem.
It is
It is the
generation, right?
generation, ith
Yes.
generation. In some
Yes.
questions you
Okay.
saw, right? Yeah, you see for in question number 7, Pi denotes the power generation of ith generator. It's not the rated capacity.
Okay. Okay.
Yeah. Okay, so
Okay.
further 10, 11 would deal with your faults, and 12 would deal with your synchronous stability. It's probably the most important topics of power system. So we'll be dealing with that in the next three these live sessions. And I will upload this by today only, this video and this file. Okay.
Thank you.
Yeah, thank you. Bye, Lakshman.
Yeah. Bye.